Okay, I'm going to show you how to get to the online book that we're going to be using for the last couple of classes. You can see the instructions here in the handout that I emailed out. First you go to books.google.com and then you type this into the search books window. So I'm going to cut and paste this into the search books window. So let's go there. First I'm going to type in books.google.com. And then in the search window, I'm going to cut and paste that search. Click on the first one. And in this book, you're going to look for Lotka, L-O-T-K-A. It tells you to go to page 435. So this is the text that we're going to be using. All right, what you want to do is make this full screen. You can see the full screen button there. Okay, sorry that the recording, the text is not so clear. But this chapter talks about a particular application of differential equations. I wanted to use this application because it's not, although it's not a very difficult application, it still involves a system of differential equations like we've been studying recently. Scroll down here and you can see the system that they use. If you see the mouse there, there's two equations in two unknowns, x and y. Both x and y are functions of t. X is supposed to represent the number of rabbits in a particular ecosystem. Y is the number of foxes in the same ecosystem. And dx dt and dy dt is talking about the rate of change of the number of rabbits, this equation here with dx dt. dy dt is the rate of change of the number of predators, which we are considering as foxes. Okay. So why do we have these relationships? Well, if you think about the rate of change of the number of rabbits, the more rabbits you have, the more rabbits you're going to get. This is a typical population growth relationship, that the rate of change of population is proportional to the population itself. That's why you see exponential growth curves for populations. You see those in math textbooks or in the news. Down here, there's a similar term, only it's negative. Now, why do we have a negative on the predator rate of change? Well, this is assuming there's no rabbits. If there's no rabbits, then the amount of foxes is going to decrease rapidly, and the rate of change is going to be proportional to the number of foxes, because they're going to die off in proportion to how many foxes there are. So that's why you have this term here. Now, this bxy term expresses the fact that if you have both rabbits and foxes, the rabbit population is going to decline. The more foxes you have, that is, the bigger y is, the bigger the decline. That's why this negative, and that's why this term here is proportional to y. Similarly, if there are more rabbits, then the fox population is going to grow. That's why this term here, the nxy, it's proportional to x because the rate of growth of foxes is going to be larger if there are more rabbits. So that's kind of a once-over reason why we have this system of equations. Now notice that unfortunately this is not quite like the equations we've been looking at before. The equations that we looked at before didn't have this bxy term. The equations, with system of equations, we had linear equations. This is not a linear equation because it has x multiplying by y. Right. But we can still use some of the same techniques to analyze this system of equations that we've used previously. Specifically, we can use this phase plot that we just recently saw and used for linear equations. All right, so let's analyze this system of equations. Okay. First of all, in order to analyze this in a practical situation, let's get back there. I don't know why it's jumping like that. Let's just scroll like that. Okay. We need to get some practical values. So presumably you could get the values for a, b, m, and n by observing foxes and rabbits. In this case, we're just going to plug in these values that they give us. A is 0.04, b is 0.002, m is 0.08, n is 0.0004. Now he says here that you want to find the values of x and y for which dx dt and dy dt are 0. Now why would you want to do that? Dx dt means the rabbit population is not changing. Dy dt means the fox population is not changing. So what that means is if we can find values of x and y such that the rabbit population doesn't change and the fox population doesn't change, what that means is that that set of values is at equilibrium for the system. We can have that many rabbits and that many foxes, and the number of rabbits and foxes won't change over time. It's equilibrium. It's not going to change. So let's see how that works. All right. So here's our equations. If we plug in the numbers, and in order to get dx dt equals 0, we need to set this top equation equal to 0. In order to get dy dt equals 0, we set this bottom equation equal to 0. He goes through and finds various solutions. One is 0, 0, which is obvious. If you have no foxes and no rabbits, they're not going to spontaneously generate. And one is 220 for rabbits, 20 for foxes. What that means is that you can have on the average 200 rabbits and 20 foxes around, and that relative size of populations is not going to change. They can coexist in those relative amounts. Okay. So in general, you'll have this kind of relationship, and for arbitrary a, b, m, and n, the critical point, what they call the equilibrium points or critical points, are 0, 0, and these values you can solve in general. All right, now suppose you're not at an equilibrium point or a critical point. What do the populations of rabbits and foxes look like changing over time? Okay. All right, so let's go back to that particular example, the x dt dy dt. And this can't be solved exactly. Usually it's solved numerically. And over here on the right, we have a solution. This top curve here that's labeled x represents the population of rabbits. This bottom curve y represents the population of foxes. This x-axis represents time, and the y-axis represents population. Notice that we saw before that 200 for rabbits and 20 for foxes was an equilibrium combination. Here we see that if we're not exactly at the equilibrium, the rabbits population goes up and down, the fox population goes up and down. And notice something interesting. The rabbit population goes down the fastest when the fox population is the largest. So doesn't that make sense? Because the rabbits are being eaten more. Now what happens as the rabbit population goes down, the foxes don't have enough to eat, so the fox population goes down. So the rabbit population recovers and starts going up again. But as the rabbit population recovers, the fox population goes up. There's a little bit of a lag. But as the fox population grows, he's going to take the rabbit population down, and so it goes. All right, so this kind of shows the relationship between rabbit population and fox population. All right, so this is representing populations as a function of time. But that's not the only way to represent populations. We use these slope fields to show the relationship between quantities that are varying, and we're going to use that here also. When you plot the slope fields, we're going to be plotting x on the x-axis. X is the population of rabbits, and y is the population of foxes. So we had two equations. One was dy dt and one was dx dt. We'll take the ratio of those two equations, and you know, according to the chain rule, that dy dx is equal to dy dt dx dt. dy dt over dx dt. All right, so dy, if we consider the fox population as a function of the x population, then dy dx looks like this. Now this is kind of a different way of looking at it. We're taking time completely out of the picture, and we're just seeing how the fox population varies as a function of the rabbit population. Now, since we have dy dx equals some function of x and y, that enables us to produce a slope field, right? dy dx is the slope. So for any x and y, I can create a slope value, and I can make an arrow whose slope is equal to that value of dy dx. For instance, if you look at this point right in the middle there, you can see that's 220. Right. It turns out that at that point, the numerator here is 0, the denominator here is 0. That's undefined. That means that there's no slope. That means it's not going anywhere. That is our equilibrium point. The field is not pointing in any direction whatsoever. On the other hand, if we found values of x and y, and we plugged into here, then we'd get our dx dy, and we would plot our slope accordingly. All right, so what's the point of these slope fields? Let's see what we can do with this. Okay. Let's use these particular values of numbers that we used before. Now here we're plotting, he calls this a solution curve. Now this looks very different from the curves that we had up top there with the, oops, sorry. I don't know why my mouse is sticking here again. I think it's something with a recorder. That solution curve looks very different from these curves as a function of time, because we're not putting time in the picture. Instead, we're seeing how rabbits vary with foxes. All right, sorry. Still having trouble here. Okay. Sorry. I don't know what's going on, but we'll get there. Okay. All right, so here's the graph I'm looking at. This shows rabbits versus foxes. And what's happening here? This curve represents a cycle. As time varies, the system travels along this curve. And the point on the curve represents the number of rabbits and number of foxes at that particular time. So what this is saying is that as time varies, down here at the bottom, say, here I have about 200 rabbits. The rabbits are increasing. And you can see the y-coordinate, the foxes are increasing also. All right, now as I go around, rabbits continue to increase. After I've gotten this point, the x-coordinate is decreasing, so the amount of rabbits is decreasing, and the amount of foxes is increasing. Up to this point, the number of foxes is its maximum, about 35. The number of rabbits is about 200. At this point, the fox population starts to decrease. The rabbit population also decreases. At this point, the rabbit population, it reaches its minimum, but from this point on, it starts increasing. So over here, he shows the 4 key turning points in this cycle. At this point on the right, maximum number of rabbits. At this point on the top, we have maximum number of foxes. At this point on the left, we have minimum number of rabbits. At this point at the bottom, we have minimum number of foxes. So he explains this cycle here. So I encourage you to read this description. He's showing what's going on with the populations. So it's very interesting that this system of differential equations can show a population relationship that really makes a lot of sense. All right, in this discussion down here, he mentions that you actually can solve for the number of foxes as a function of number of rabbits. There's an implicit relationship that relates the foxes to the rabbits. But this doesn't give foxes and rabbits as a function of time. We're not going to talk about this much. I don't believe any of the exercises deal with this. So let's go on to the next page. Okay, so here we have another case of 2 different species. Here we have a case where we have one species, population x. The rate of change of the population x also is proportional to x, but the thing is that if x becomes too large, then the population starts to decrease again. Okay, that's the significance of this next term. Here we have a similar situation, another species where you have the population of y increases in proportion to y, But if y becomes too large, then we start getting a decrease again. Now suppose these two populations are competing, which means that if the more x's there are, the worse it is for y. The more y's there are, the worse it is for x. That means that we add this other term here, which reflects that relationship. The more y's there are, the more negative this term is, so the larger effect this has on the growth rate of population x. The more x's there are, the larger this pxy term is, so the larger the effect on the growth of y. There's a different set of differential equations, and the discussion for this is quite similar to the discussion for predator-prey. We can still look for critical points, and these will be the points where both dx dt and dy dt are 0, and that will be an equilibrium that the two species can coexist in those relative proportions indefinitely. So he solves the equation 0 equals ax minus bx squared minus cxy, and 0 equals my minus ny squared minus pxy. And he comes up with these critical points. He doesn't actually do the computation, but it turns out that these are the critical points. Okay, let's go back. Okay, he does go through a somewhat long discussion. That's more technical, so I'm not going to talk about that. All right, so here's one example of equations for two competing species. You can find the critical points, and you can use some graphing utility. I will show you how to use a graphing utility in the class. Very nice way to show how you can write these equations and show how the two populations change. And in this case, he ends up with a result that population X dies, population I goes to its stable point. Okay. So the behavior of the two species is going to depend on what constants you put in on the right-hand side. Here you have this set of constants. In example 7, he changed the numbers a little bit and found out that X and Y could end up coexisting. Let's see if we can get down there. Looks like they end up coexisting at a stable level. Okay. So here he talks about critical points. Here he draws the slope field. We will have a software to draw those slope fields for you. Okay, and then we get to the exercises. So that should be a good introduction for what we're going to be doing in class.